Hey, y'all, it's Gilsdorf. We are going to be looking at waves calculations. And so I tried to connect my camera. It didn't work. So now you just got this awkward video of me leaning on the counter and doing calculations with you. But obviously I'm not here, but I want you to feel at least a little comfortable with starting these calculations. So I'm going to go through them a bit. We've talked now about the fact that waves are represented with their frequency, which is the amount of waves that pass a certain point in a certain amount of time, usually measured in per seconds or hertz. And so hertz is a unit that means per second. So it's basically seconds to the negative one. The other two, wavelength is typically measured in nanometers or meters. And then energy measured in joules or kilojoules. And the speed, which is speed of light, 3.00 times 10 to the 8th meters per second. Okay. So those are kind of the variables that are out there. They all have some sort of relationship, which means they have a mathematical relationship. That mathematical relationship is represented here. So we have wavelength, which is represented with the symbol lambda. And then we have frequency represented with the symbol mu, and the speed of light represented with the symbol c. Now, I'm going to be doing some things on my paper. I recommend you probably do the same thing. I have a couple different colors here. So I'm identifying that my speed of light is going to be a specific color. And so what I've done here is identified up here at the top, where is everywhere that shows up. So I chose pink. If you need to pause so you could do this to your paper, go right for it. But the speed of light is always the same, and that is 3.00 times 10 to the 8th, and it is at the top of the equation. The other variables that we are mentioning are wavelength. So I'm going to represent wavelength with a different color. It does not matter what color you use. Oh, also, yeah, please go grab the highlighters from the cabinet that says markers and color pencils if you need them, okay? Wavelength is represented again with the symbol lambda. Typically, if you're solving for wavelength, that's what you will use, and I'll show you in a second what we do for frequency. And then frequency is represented with the third color, okay? So when I'm looking at this, I have the speed of light, which is always the same. That's why I highlighted it right at the top. And then wavelength and frequency. Now, when I am running these calculations, this is just like the density formula where you can manipulate the formula based on what you need. And so I'm going to just go ahead and draw a couple things on here. So if I am solving for wavelength, right here, then all I need to do is take the speed of light and divide it by the frequency. If I'm solving for frequency, all I need to do is take the speed of light divided by the wavelength. If I, for some reason, was solving for a variable which is constant, then I would multiply these two, but we don't, it's a constant, right? So when I start going into the first problem, before I do that, so we've already said that the speed of light, I'm writing the units on here, are typically in meters per second. The wavelength is typically going to be in nanometers or meters, and then frequency is in hertz. However, I'm going to circle meters over here by wavelength, because the problem here is if a problem asks you for the wavelength in nanometers, lovely. But if you are running a calculation with the speed of light in meters per second, then they need to be in the same unit so that they'll be able to cancel out. That's what unit conversions are about. So if you are running a wavelength, it needs to be in meters to plug it in. If you are solving for wavelength, then it's going to automatically come out in meters. So you don't have to worry about that. So I've identified in these problems that there is, number one is a little harder than number two. So let's start with number two, okay? So when I look at number two, it says green light has a frequency of 6.01 times 10 to the 14th hertz. And so what is the wavelength in meters? Well, frequency was yellow, so I'm going to highlight it in my problem. Frequency of 6.01 times 10 to the 14th hertz. And then wavelength is orange on my paper. So I am going to highlight that. So that's what I've done here in number two to identify what we have and what we're looking for. So I'm looking for orange. I have yellow and I have pink because pink is always the same. So if I'm looking for orange, I can just plug it in as it is. So I'm going to go ahead and put my, wrong spot. Don't judge me. Lambda equals C over mu. Mu is basically just kind of a lazy V. It's not that important, but there you go. Okay. And so C is always the same. That is 3.00 times 10 to the 8th meters per second. And then for V, I'm going to plug in the frequency that was given to me in the problem. So 6.01 times 10 to the 14th hertz. Okay. And so what we have here, we've said a couple things now. We've said that We have a frequency. It's in hertz. Hertz is, again, meaning basically per second. So if this is meters per second and this is per second, then if I'm running this calculation, meters per second and hertz cancel out, and that's how I end up with just meters. Okay. If you were like, well, it's a wavelength that's going to be in meters, right? Cool. But I just wanted to show you how it canceled out. So if I run that calculation, I'm going to put that in my calculator, and I'm going to show you how I'm putting it in my calculator, because my experience has been that most people that make mistakes are making the mistake when they put it into the calculator. 14. Okay. So on this paper, it is 3.00 times 10 to the 8th divided by 6.01 times 10 to the 14th. So that is exactly how I have, well, kind of. It's hard. There you go, kind of. That is exactly how I put it in the calculator. Be careful with the E function. It is good to use it. However, some people are putting times E, and what that does is add an extra times 10. So the E basically stands for exponent. You put in the base, and then you just put straight to the exponent, and your calculator knows what it's doing, okay? So when I run that calculation, I'm hitting the wrong button. When I run that calculation, I get this crazy calculation, which may or may not come into focus at some point in time. You can see it on your calculator if you set it up the same way as me. So it is 4.99 times blah, 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 E negative 7. So when I go to write that down, I'm going to check my sig figs. I need 3 based on the problem. So 4.991 is just going to be 4.99 times 10 to the negative 7th. And since we ran this with meters per second, the unit has come out to be meters, and I am done. So at that point, my answer, 4.99 times 10 to the negative 7th. Okay. So if I go back to the first one, so I want to jump back to the first one. We are using the same formula, lambda equals c over mu, or wavelength equals speed of light over frequency. But when I go into my highlighting on this one, I realize, okay, so I have wavelength of 4.10 times 10 to the negative 6 nanometers. That's orange. So I'm going to highlight wavelength of 4.10 times 10 to the negative 6 nanometers in orange. I am solving for my frequency, which I have chosen yellow. So that is what I am solving for, is the frequency. However, we said that nanometers needs to be in meters if we are using it. Because nanometers, that's cool. That's a unit of measurement. It's just a very, very small one. But if we're measuring the speed of light in meters per second, we've got to make sure that the unit of length or the distance is actually the same. So we have to make sure that's also in meters. So in this case, this is going to be a 2-step problem. I need to do kind of a side calculation over here where I convert it into meters, and then I can actually run the calculation. So my first part, and I'm literally going to do that way over here to the side of my paper, 4.10 times 10 to the negative 6 nanometers. And according to our notes, the section of notes, which I don't have present, but you have, according to our section of notes, it says that one base is 1 billion nanometers. So what that means is 1 meter is 1 billion, or 10 to the 9th nanometers. And so that is what I can put in. So I can say, okay, I can either type in a billion, or I can make my life easier and know that it's moving the decimal 9 times. So I'm going to say, setting up my conversion. I've set up my conversion like this, 4.10 times 10 to the negative 6. And I'm going to end up dividing that by the number of nanometers in a meter, and that'll get me my answer in meters. Because whatever answer comes out of there, squiggle, 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 that's what I need to plug in for wavelength. Okay? And I already noticed that this is solving for wavelength. If I need to solve for frequency, then I need to adjust this a tiny bit. And so that's what I'm going to do. I'm going to say, all right, well, based on this, frequency is speed of light divided by wavelength. So that's what I'll write. Frequency equals speed of light, or c, over wavelength. So there's my formula that I'm going to be working with now right here. I've adjusted it, just modified it a little bit, and I'll be able to plug in that value for the wavelength there now. So that's where it's going to go in the bottom. I have c, I'm looking for frequency, so let's plug in and go. C is 3.00 times 10 to the 8th meters per second. Wavelength is, I didn't calculate it, but I can figure it out pretty quick. 4.10 times 10 to the negative 6. So 4.10 e negative 6. divided by 10 to the 9th. Now, this is a part where I made a mistake in front of third period. How fun. But I made a mistake with this. So if I'm going to put 10 to the 9th in, I'm going to put in something you absolutely cannot see. I'm going to put in a parentheses, okay? And then I'm going to do 10 caret 9, okay? My calculator's fancy, so it's trying to actually make it into a caret. Sorry, you can't see that. So I did 4.10 e negative 6 divided by parentheses 10 raised to the 9th, close parentheses, okay? Otherwise, your calculator's an idiot. It doesn't know. So the number I got was 4.10 times 10 to the negative 15th meters. So here's where I'm at right now. Speed of light, c, divided by the wavelength. I'm going to run that in my calculator. So 3.00 second e to the 8th. And yes, I am aware that there is a shortcut with exponents. And if you know how to do that, great, do it. Dividing, you subtract them. Multiplying, you add them, great. You still have to do the base calculation, whatever, okay? So if you're comfortable with that, go for it. This one gives me a very large number, which again, I'm going to hold up and you are not going to be able to see because oh, there it is, okay. So it gives me a very large number, 7.317, blah, blah, blah. Based on sig figs, I need 3. So I'm going to say 7.31, and then I see it does have an E22. I can't leave that out. So that's times 10 to the 22nd. Frequency is in hertz, okay? So this is the answer I ultimately get, 7.31 times 10 to the 22nd hertz. And again, if you are interested in understanding how the units happened, it was meters per second over meters. Well, if both of the meters cancel, then we're left with per seconds, or seconds to the negative 1, which is what hertz is, okay? So what I would like for you to do, run through question number 3, question number 4, and then 5 and 6, because those are just reviewing the electromagnetic spectrum. And then on the back, this is where I want to push us a little bit, okay? So this is the calculation for actually calculating the formula for calculating the energy in a wave. And so see what you can work with this. There's nothing going to be major different. You notice there's 2 formulas, whether or not you have the frequency or the wavelength. Slightly different, but not huge. There's a new constant here. Who cares? It's a big number, but we know how to punch numbers on a calculator. That's all we're doing, right? So try to run through a couple of these. If you can get through all of them, fantastic. If you can get through one of them and you don't have a breakdown, fantastic. Check the answer key. And then on Monday, then we will come back together. I'll make sure that we're feeling decent with it. I'll give you a chance to kind of split up based on how you're feeling with stuff. And then we'll launch into our next topic. Okay. So don't feel like you need to master this just yet, but please push yourself to make sure that you're feeling decently comfortable with it. And I will see you next class. Thanks.